Good morning, it's Jeremy. It's Thursday, March the 7th. In a previous video, I looked at generating random data in GNU radio, and here's the schematic I used. Then I used that random data to feed a VCO, to set up a VCO. And today what I'm going to do is I'm going to take the waveforms, the random data, and the VCO output. I'm going to test a BFSK decoder. So let's just run this circuit here for the random data, just to recall what happened. So there's the random data output. I can stop this, increase the scale a little bit. So there we go, there's our random data waveform. And let's go to the VCO. So there's the VCO. What I do is I take the random data that I've just created, I stored it in a file, a DAT file, and then I discussed previously how we set up these constants, and that'll drive the VCO. So the idea is that a 1 will produce the DSC channel 70 mark frequency, which is 2100 hertz, and the 0 will produce the space frequency of 1300 hertz. So let's just run that. All right, so there we go, that's what's going. There's the random data, and we can see under here that when it's the 1, we get the higher frequency. When it's the 0, we get the lower frequency. Okay, so I've created the data and the BFSK waveform. So now let's look at a decoder. So the first decoder I'm going to look at is this guy here. So I'm going to take the wave file input that I've just created and the random data. Now, previously we discussed the types of decoder for the DSC signal. Unfortunately, the DSC signal is not orthogonal in the sense that we can use a coherent detection scheme. So we have to use either a bandpass filter or an IQ type of demodulator. So that's what I've set up here. I've set up a bandpass filter type of scheme. So the first bandpass filter is at the mark frequency of 2100. The second one is at the space frequency of 1300. And what I do is I take the output of the bandpass filters, I square them, and then I go through a low-pass filter. So the operation of squaring a low-pass filter is essentially an envelope detection process. And then I subtract the two. So positive pulses indicate that you've had a 1 or a mark, and negative pulses indicate that you have a space. And then what I do is I sample and hold. So let's look at that. I've got multiple scopes here just to check everything. So if we look at the first scope here, let's increase the X here. And we stop that. There's my input waveform. And there's my decoded output, and you can see it's the same as the data that's coming in. So that's basically the operation there. And then the other thing I have set up here is I have another decoder. And on this decoder, what I'm looking at is the, where are we here? Yeah, this is the channel 70 off-air waveform that I recorded previously. This is not, I didn't create this waveform myself. This is from an actual station. So let's run that and see how that works. So I'm going to increase the X here. So let's just take off, yeah. So there you can see these are the pulses from the bandpass filters and the envelope detectors, and you can see that these are the bits coming out here. So that seems to work. Anyways, what we've done then is we've looked at decoding the DSC signal in GNU radio. Previously, I'd done everything in Psychos. The advantage of GNU radio is that it's a real-time type of decoding, and you can use it with the RTL SDR. So what I think I'll look at next is probably try and build the IQ decoder in GNU radio, and after that we'll start streaming the data. So in other words, we'll take the output and probably go up into the next level. Right now we're at level 1. the physical layer. So we'll probably get up, try and get it up into the data link layer and do some work there next time.